What if I told you that the yellow you're seeing on the screen is not yellow at all? What you're actually seeing is just a mixture of red and green photons hitting your eye. This illusion points to a fundamental limitation of not only your eyes, but also cameras. Which for everyday pictures this is fine. However, for certain use cases, this loss of information is detrimental. For example, for my use case, where I want to predict the chemical properties of grapes on a large scale to automate harvesting or to precision visual culture, this detailed information is necessary. Such use cases necessitate the need for different tools. Luckily, we have hyperspectral cameras. However, because we look at light in such a detailed way, we become more dependent on the overall illumination of the scene. Traditional methods have tried to tackle this by using wide reference calibrations to normalize the spectrum in order to become independent of this illumination. However, these are burdensome and impractical for large-scale operations. Luckily, we developed a data-driven approach that's also more independent of these illuminations while still being scalable. We achieved this by using a custom robotics platform, taking it in the field and capturing a dataset under real-world conditions. We then trained a more robust algorithm using an adversarial learning approach and incorporated into an overall pipeline that's able to predict quality and yield in real time on the edge. Now let's look at each of these in more detail. Here you can see my colleague and me in the field capturing a dataset with our custom hardware. The custom hardware is made out of a base platform, the TreeBot, which is robust and able to traverse the uneven terrain of the vineyard. On top of that, we have the universal robotics arm, which is holding the hyperspectral camera. In this case, an FX10, which only scans one line at a time. However, we can easily see that by using the movement of the robot, we can generate the second dimension of the hyperspectral image. We then combine the hyperspectral image with the coordinates to be able to localize the gray bunches. During our data acquisition campaign, we captured datasets in the morning and the afternoon, as well as under lab conditions, resulting in 3 distinct illumination conditions. Training some early predictive models, it quickly became clear that training on one dataset and predicting on another, the performance degraded significantly. This so-called domain shift sparked the idea of creating a more robust algorithm that's more independent of these illumination conditions. So we developed the light invariant spectral autoencoder, which is a deep learning approach trained end-to-end using adversarial learning and a composite loss. The encoder takes in a patch of hyperspectral data and compresses the spectral part. The latent space is then given to a domain classifier, which we do not want to be able to classify from which domain it comes. We give it to a task predictor, which we do want to predict the Brix or acidity, so the sugar or the acidity of the grapes, to make sure the information needed for such predictions is still in the latent space. We have the manifold regularization term, which clusters objects of similar chemical properties closer together. Finally, we stabilize training by incorporating the reconstruction loss. However, such a robust algorithm on its own is useless. We have to incorporate it into a wrapper that's able to use it efficiently. So we developed a pipeline that's able to predict quality and yield in real time on the edge. Here you can see the robotics platform traversing through the vineyard, generating a long sweep of data. On this, we use a sliding window, of which the window we give to a YOLO object detection algorithm, which gives us gray bunch bounding boxes, which we use for unique grape IDs. We then locate the gray bunches back on the hyperspectral image, and then give the hyperspectral gray bunches to the light invariant spectral autoencoder, which then predicts Brix acidity and whether or not the patch came from the gray bunch or not. We give the hyperspectral gray bunch the weight predictor, and then combine it with the coordinates, store them in the database to be able to do precision viticulture and yield estimation. So we saw that capturing the dataset under different illumination conditions sparked the need or necessitated the need for a more robust algorithm that's able to be independent of these illumination conditions. So we developed the light invariant spectral autoencoder, which does this while still being scalable. We incorporate it into an overall pipeline that's able to predict quality and yield on the edge. And with this pipeline, we are one step closer to automating or to scaling up these robotics platform in the field and doing precision viticulture or automating harvesting at a large scale. And so with this data-driven approach, let's hope that the smart farmers of tomorrow are less easily fooled by light as we are.